All right, so here we go. So the title is Transmit Only for Dense Networks. Hope everyone knows I'm Bernhard Firner. I'd like to thank my advisor for an excellent introduction. Let's say I've been here 7 years. Of course, I'd like to thank the committee for showing up, and for everyone else for showing up as well. Here we go. So, let me talk about one half of the title. What do I mean by dense wireless networks? Well, so as we know, wireless devices are getting cheaper, which means there are more of them. Everyone here probably has a cell phone. Maybe some of you have two. Maybe some of you have a cell phone and a laptop. You already have two wireless devices. But in the future, we're talking about not just having wireless devices that you use as a mobile computer, but wireless devices that you're putting on everything else to gather information. So if you've ever heard something like machine-to-machine communication, Internet of Things, Internet of Everything, ubiquitous computing, any of those terms, they're all about making more and more small, tiny wireless devices, putting them on more things. So Cisco on their website, they have this silly little screen that's just a number rolling up every second. They estimate that by the year 2020, there'll be 50 billion devices. Now obviously a lot of these are not going to be attached to a person because they only estimate they're going to be something like 10 or 20 billion people by then. So a lot of these are going to be stuck on something else. They're going to be used for things like smart homes, monitoring. Maybe you'll put them on every single chicken or every single cow on your farm, doing some kind of livestock monitoring. Right, so what kind of characteristics do these have? That's what this topic is about. That's what the thesis is about. It's just about dense wireless networks. So, what are these radios doing? They're frequent periodic transmissions. Let's say they're gathering data, maybe once a second, maybe once a minute. They're small packets, just a little bit of data. So let's say you have one in the greenhouse, maybe it's reporting temperature, humidity, that's it. It's not a lot of information. They're not watching YouTube, right? So the data is probably fairly redundant. So again, let's say you're monitoring something. The data that you're monitoring probably doesn't change that quickly. So you're going to see sort of very similar data patterns over and over. So now there's a problem. These are small mobile devices. I just said we'd like to stick them on everything. The small mobile devices obviously don't have wires. They're running off of batteries. Now here's the issue. This battery has to run for years. Now as all of us know, your cell phone or your laptop doesn't run for years on its battery. So, is this a problem? The answer is yes. So here we have 3 different lines and a pretty graph. So this is the seconds of radio usage that you can use per day. That's the amount of time you can leave your radio on every single day, and to achieve some amount of lifetime on the x-axis. So now let's say you have maybe a coin cell battery, bigger coin cell battery, or AAA battery. Once you get to a lifetime of 10 years, the total amount of time you can use the radio per day is in the seconds. If you're running on a little coin cell battery, you have less than 10 seconds of radio usage per day, which means you have to be very, very sparing with it.
And what kind of radio did you assume for those curves?
We assume the CC1100 drawing, actually we assume any radio drawing 20 milliamps during transmit or receive. And I'm not taking into account the energy consumption of the microcontroller. So that's just the radio. I'm not assuming there's any processing or anything else. So this is actually rather lenient, because generally you'd have to spend energy doing something else as well. So let's say you're just using the radio. So existing MAC protocols generally weren't designed to be energy efficient. They're designed to worry about reliability and throughput. Right? If you're watching YouTube, you care about getting lots of data, you care about getting the packets. Right? You don't care that your phone will die in an hour, you want to see that episode right now. But it's not good for this kind of thing. Really what these things need to do is sleep. Almost all the time they need to turn everything off and draw as small amount of power as possible. Now everything else that these things do, let's say you have a CSMA system, a TDMA system, they all have a little bit of overhead. Right? So normally an ACK packet is very short, don't worry about it. What if your data packet is around the same size as the ACK packet? That ACK just doubled your energy consumption. Same thing for carrier sensing. Carrier sensing is quick, it's a few hundred microseconds. Well, so is your packet. But maybe it's not smart to do all those extra things. Maybe we should spend more time sleeping. So that's the idea of transmit only. So the idea is we're going to save energy by only transmitting. We're not going to do anything else. No channel sensing, no coordination, no talking to anyone else. All we're going to do is wake up, send our data, go back to sleep. It means we get more time to sleep, which means we'll run longer. Now, you probably think there's a problem. You're probably going to have poor reliability. We are trading off some reliability for lifetime, but we're not sacrificing a lot of reliability, just delivery guarantees. We're not going to sacrifice total throughput, as I'll show you in a few extra slides. What we're doing is we're going to probabilistically reduce packet losses rather than giving you a guarantee by taking advantage of something called the capture effect. We're going to use multiple receivers to increase this likelihood. Now I need to explain to you what this kind of network looks like. So it's going to be one hop. Right? So we're going to have a bunch of transmitters, a bunch of receivers. They're all going to be in range of one another. So this is not a multi-hop mesh network. None of that. The receivers are going to either be wired powered, or they're going to have much more power than the transmitters, because the receivers are going to need to keep listening all the time. The receivers are going to forward the data to some kind of aggregation point. Right? So we might imagine if you have some kind of agricultural monitoring system, let's say in several greenhouses, you might have transmitters dispersed throughout the greenhouses, and maybe a few receivers in each greenhouse that are plugged into, let's say, a LAN cable with power over Ethernet. That kind of thing. Multiple receivers will be able to hear each transmitter, and that's how we can increase the likelihood of the capture effect. Now, I've set the capture effect on a couple of slides. I need to tell you what it is. So sort of the whole linchpin to transmit only is that we can take advantage of the capture effect. So the capture effect isn't something that lots of people talk about, so I need to explain to you what it is. So during a packet collision, packets have different signal strengths. Let's say one of them is very strong, one of them is very weak. Now it happens that the stronger packet may be captured, and the weaker packet simply lost as noise. You'll still lose one of the packets because it was in a collision, but actually the stronger packet is still saved. So you might think of it like this. If we have transmitters A and B, they both transmit. If this is their power level, it's strongest. A's power level is strongest where A is. B is the strongest where B's is. And in this region, A's is stronger, so you capture A's packet. In this region, B's power is stronger, so you capture B's. And somewhere in the middle, when their power is about equal, you won't capture either one. How is this useful? Well, so imagine we have these transmitters A and B. Imagine this is their power level, decreasing as you go further away from each one. Now, the receivers in the center, like I said, they collide because they transmit at the same time. You lose both packets. Let's say instead the receiver was closer to one of them. Well, then you'll receive that one's packet. Now let's say instead of just one receiver, we have two receivers. Well, now you receive both packets. Two transmitters, they both transmit at the same time. We had a collision, but we actually received both packets successfully. Now I'm not saying we have to have one receiver for every single transmitter, but having more receivers increases the likelihood that you'll capture all of the packets. Because remember, we don't have to have one receiver for every single transmitter. Just during a collision, we'd like to have one receiver for every transmitter involved in the collision. So, to sort of explore the capture effect a little bit more, I did a case study with the CC1100 hardware. So it's a sort of common low-power hardware. If you see it in your PIPs around the lab, you'll see they have them. It's a little tiny chip. So what I did is I had them collide the packets over and over again. I want to use it to describe when exactly capture occurs. And these are some details about what was being sent to make Giovanni happy. But I think that's enough for everyone else. So basically, this is bit error rate, and this is the difference in signal strength between the two transmitters. Over here, the transmitter was weaker. Over on this side, our transmitter is stronger than the interference. So now the bit error rate of 0.5 means that you're guessing the bit. Was it 0 or 1? You don't know, you guess. Right? So that's where the bit error rate is 0.5. Over here, it falls down to 0, which means you're correctly receiving the packet. So now the capture effect is not really a binary thing. It's not you either magically get all the packet or you don't. It's a little bit of a probability, right? Because it actually has to do with whether or not you successfully got every single bit. But once you get to around 6 dB, your error rate is basically 0, and let's call that the capture threshold for the CC1100 radio.
So before you go, can you describe what the bit is? What's ERFC?
Oh, this is just an error function fit, because we're assuming there's some. Basically, it has to be an error function curve going from no information to getting all the information. And you notice there's some jitter here as well, and that has to do with how the experiment was set up. And there are way more graphs about this in the thesis. So if everyone wants to see exactly why it jitters and those other things, all the explanations are in the thesis. Or I could stop for 10 minutes and explain, so that's not. So anyway, that's the capture threshold in the CC1100 radio. But other radio hardware is very different. So for instance, there was another study that looked at some Etheros wireless cards. And they're as good as 1 dB. And I've read some other data sheets that claim like half a dB, but I'm not sure if that's true. So let's just list those two as sort of examples. And for the purpose of talking about the sort of the upper bound of the performance of a transmit-only system, I'm going to label a 0 dB threshold as perfect capture. So this means whenever there's any collision, you get at least one of the packets. Even if it doesn't matter what their power levels are, you'll always get one, even if they have the same power level.
Quick question about the measurements of bit error rate. You used the CC1101 to get 6 dB. You used error correction, right?
I mean, how did I check it? Or I just had data whitening, didn't have like error correction. What I did is I knew what the correct packet was going to be, and then I checked what I actually received. So because I knew what the correct one was, I could actually count every single bit error.
Okay, so you're able to achieve reasonably good, reasonably low bit error rate with a 6 dB signal to interference ratio and no error correction?
Mm-hmm.
That's a bit surprising.
With the CC radio? That's, what, 4 times the power? It's actually not that amazing because, I mean, unless you mean by it's amazing for the CC1100.
That's what I mean.
Okay, maybe it's amazing for the CC1100, but for, like I said, like 1 dB on some commodity Wi-Fi cards is, I know Wi-Fi cards are more expensive than the CC1100 is, but I mean, I think this looks pretty bad. So anyway, so now that we know what the capture effect is, let me talk about how we can actually utilize it to make
But
TL
you
an
know,
awesome system.
where you show them as 0, right? They're not really 0 on the previous graph. I mean, you
Here?
just have them all looking at 0 because you didn't plot in log scale, right?
Oh, you mean the bit?
Because
Actually,
your scale, you can't tell 10 to the minus 2 and 10 to the minus 3. But
also, I also don't know what the bit error rate of the over-the-air channel is.
what do you mean
So
by
it's,
the bit error rate of the
Well,
over-the-air channel?
I guess the best way to put it is the bit error rate over here is indistinguishable from the bit error rate over there.
What do you mean it's indistinguishable?
So the CC1100 is not a great radio, and sometimes it simply fails to receive a packet. Right, so I can't, at this point, I can't distinguish this point from that point. Right, so on this hardware.
It's not a capture effect loss.
Right.
Yeah.
Even if you had nobody else transmitting, you may still lose bits.
It's purely a, so the radio actually has glitches in it and the state machine that cause it to lose packets sometimes, and seems to have other undocumented effects that cause it to lose
So, but
packets.
if you really ran it a long time and collected a lot of bits, right, then you would get a number.
Yeah,
Right?
and so,
But you're saying, oh, the number at 6 or 10 is the same as the number at 13 because
You're saying you want
there's
to
all
know-
kinds of things going on
Yeah.
in this radio that are.
I mean, I have the data, I could look at exactly what the error was at those points. It was very low, at least 2 or 3 places out. So it was very far below, very close to 0.
Ben, this was with a payload of 16 bits, if I remember from a previous slide, right? So when you
Yes.
go down to a bit error rate of the order of 5%, you get a significant probability of the packet being good.
Yeah. So what I did is I had them transmit the packets over and over again for, I forget how quickly it was many times a second, maybe 100 times a second. It was either 100 or 1,000. I had 2 radios wired together, so when one transmitted, it told the other one it was transmitting over the wire, the other one began its transmission. So I just repeated it, let's say it was 100 a second, because I don't remember it now, it's in the thesis. And I left it on for 10 minutes at a time. So there were quite a few packets. So it wasn't, I didn't just sort of slap it in. The reason why there is jitter in it is because there are different regions of collision depending on the area of the packet. So the packet's not all just data, right? There's a preamble, a sink, and then the data section. And depending on where exactly the interference occurred, you see a different kind of packet loss. So I tested it against those different regions. So when I combine the data, there's some
that's not
spots
the
where it's
interesting
a bit
part up there.
Yeah.
Up there, I went down over here from 6 onward.
This
You're
little
calling them
jitter.
all the same, but I'm saying, you can demonstrate they're all the same if you take enough data points and
Yeah. No, I have the data.
plot it in the right scale, but you can't tell from your plot. Your plot just hides the truth of whatever is going on.
I will email you the data and a log plot.
You know.
I do have it lying around, so I can check. Did you have a question? Now?
Yeah, so you said previously that no error correction code was applied.
Yeah.
So then what's the distinction between preamble and payload?
So the preamble is purely used for power detection. Then there's a sync word that's a series of bits. That's
Okay,
not
so
that.
you're not checking the bit error rate on the preamble.
No, because the radio doesn't
They're
tell me
not
anything.
sync
Yeah, the radio
on the-
doesn't tell me anything. There is a sync word where it's expecting a certain pattern, and it allows at most 2 errors. So I did check that. So I knew the probability that it got every single bit or got all but one bit correct in the sync word. But it doesn't actually tell me any other information other than that. So the CC radio doesn't give a lot of information about what it's doing.
Ben, I have two quick questions. One is, when you're talking about overlapping packets,
Yes.
these are packets that overlap even partially. In other words, sometimes they overlap completely, sometimes they
Yeah,
overlap
so I went
only
through
partially.
every single different overlap phase.
Okay, so there is, among those numbers, there are situations in which the packets overlapped only for a small portion of the total packet, right?
Yeah.
He actually considered many different situations.
Yeah. And I left them out here because it's...
And do you include totally lost packets or not in
Yeah, I
those
do.
numbers?
So if it doesn't detect a packet at all, that must mean that the sync word or the preamble was missed. And so because I knew how it was colliding, I knew whether or not it was colliding in the preamble or the sync word. So we could count that.
So you counted
Well, I
as
couldn't count the preamble
0.5 bit
because
array.
Hmm?
How do you count it? As,
Well, so I knew that if it missed the sync word, it must have missed at least 2 bits. Right, so I could do the probability for missing at least 2 bits. But really, most of the bit error rate really does come from just the data section, right, because that's the easiest one to count. The other ones don't give you much information. Are we all happy with this one? Or if not happy, are we satisfied?
I'm ready, I think I'm ready to move on.
All right. I don't know.
All right, let's move on.
Okay, let's move on. Okay, now we can talk about TO's performance. Okay. So one question you might be thinking to yourself, well, maybe I don't know if anyone is, I'm using multiple receivers. And usually when people use multiple receivers, they start sticking them on different channels. Why would I stick them all in the same channel? So really quickly, I just want to show you that using them on one channel is actually better than on multiple channels. So the other thing I'm going to show after that is want to compare to the existing MAC protocols, specifically CSMA. And the big metric there will be joules for every single successful bit. This is actually more energy efficient at around the same throughput. So why shouldn't we use multiple channels? Well, we can do a quick experiment and I can demonstrate how TO using the capture effect is more powerful than spreading our data across multiple channels. So what I did is I took 100 transmitters, I put them in a little 7 by 7 meter area in the orbit room actually, and I put down 8 receivers. So the transmitter offered load of total 30% offered load of the channel. So now I tested every single different combination of these receivers across different channels. So TO would be one channel with 8 receivers on the same channel. I also tested 2 channels with 4 receivers on each channel, all the way over to 8 channels with 1 receiver on each one. So that means this is 1 receiver with just 12 or 13 transmitters, versus 100 transmitters on the same channel with 8 receivers. Right, so I did some math, and I want to show you the math. All the math's at the end. And this is what I predict the outcome to be. So in the beginning, using multiple channels is actually a little bit better. But eventually, the capture effect, because it's cumulative, right? Whenever there's any collision, every single receiver on the channel gives you another chance to capture that packet. When you get to a high enough number of receivers, it becomes very powerful. It should drive the packet loss down far, far below what you get by spreading across different channels. All right, so this is the theory, and here's the experiment. Very, very close. Keep in mind this is on a log scale, and over here this prediction between, this is the actual single channel with transmit only, and this is predicted with transmit only. They're within 1% error rate. So this line right here, the brown and black lines, those are the predicted and observed multi-channel ones. So that means we have 12 or 13 transmitters on one channel with 1 receiver. And so we started off with having them all on the same channel, and then we go to having 4 receivers, and we split all the transmitters across 4 channels. So that means we have 25 transmitters on each channel. Then we get to the very end, we have 12 or 13 transmitters on each channel, and 8 receivers across all those 8 channels. As an alternative, we stay on the same channel the whole time, and we just add another receiver. And if we do that, slowly the capture gains build, and it's a better way to do things. So that's why TO is better than spreading things across multiple channels. So we want to keep things on the same channel, because the capture effect becomes more powerful as we add more receivers.
So what's the intuition behind that? It seems the naive assumption would be, as you said, they're equivalent.
So the reason,
Why are they spreading out? Like, what's
it's
the,
because if you look at the math for it, the receiver is in the exponential or something. So basically, imagine there's a packet collision, right? Now if I have one receiver on the channel, at most I can get one of those packets. It's the best I can do. I can only capture one. Now if I have 8 receivers on the channel, I get 8 chances to capture each of those packets that collided. So now, with just 12 transmitters on a channel, you have a low probability of a two-way collision. But the best you could ever do is get one of those packets. Now let's say we have all 100 transmitters on the same channel and 8 receivers. The probability of having anything more than an 8-way collision is really low. Right? There's a tiny chance. And any collision that we have 8 chances to decode it. Right? So what happens is we get so many chances to successfully decode something via the capture effect that once we get to some number of receivers, it just becomes really powerful. Whereas with one receiver on a channel, you just don't have that much luck.
yeah. Well, I don't know if I get into here, but there may be a, you can take it offline. There's an argument for queuing theory about why you want to have one long queue rather than n shorter queues. Right? Because you may not have an idle server,
Yeah.
right? So this is a similar kind
Yeah.
of argument.
The math also shows really quickly why.
But then 8 is also sort of a magic number because the probability of having A-way collision is still there, but probability of having 16-way is so small that if you have 16, maybe it's better to have 2 channels at 8 on each, rather than all 16 on one.
Maybe it does depend. So obviously if we get
8
the
has, so you only looked at a small number of receivers, we have this, but if we have 16 or 32, the comparison is not clear.
it could be if you have an over-precisioned number of receivers, it might make
Right.
sense to spread them across multiple channels.
Well, no, but getting back to the queuing theory argument, right, that if you spread out the receivers on multiple channels, you may have receivers that are idle when there's a collision. Okay?
Yeah. So
Right?
then the
Whereas
receivers
if all
are
the receivers
don't
are in
work.
the pool, then you won't have this like idle behavior.
Yeah, so it's true. When you have all 8 receivers in different channels, they're often idle. Did you have
It
a
also has to do with indoor propagations. If you assume that things fall inverse square, it's less advantageous than if you assume inverse third or inverse fourth power.
Yeah, so I should
That
mention,
also plays a
in
role.
this room, alpha was 2.64. So that's propagation. So.
Apart from that, so any propagation assumption, does this assume some sort of spatial diversity?
So the receivers have to be placed in different locations. So obviously if we put the receivers in the same spot, they'd be pretty useless. And actually we're going to get to receiver placement at the later part of the thesis. For this one, we just sort of spread them out evenly according to a paper that I cited from Rich about spreading things out to get best RSS coverage. And later on I started worrying about how you could choose the best receiver placement. But obviously, if you chose these 2 receivers to work together, that would be a less good idea than choosing this receiver and this receiver because they're farther away, so they see very different environments. Right? So the better spatial diversity you have with the receivers, the better the capture effect will be.
So do you think you get the same result if you had, it's 100 transmitters you're using?
Yeah.
You had 200 transmitters and 16 receivers, you get the same curve?
No, it wouldn't be the same curve.
So what's the difference?
So if they were transmitting at, do you want them to transmit at the same rate or transmit at half the rate?
No, transmit the same rate. 200 transmitters and 16 receivers. That
So
have
you-
the same performance as 108.
I have some graphs that will answer this question.
We may be a different load then?
Yeah, it would be a different.
Nominally, it's kind of the same. Well,
no, it would be a different-
transmitters in the area of one receiver.
It would be a different offered load. So let me think actually. If you double the load, it actually depends on the duty cycle. So depending exactly on what the duty cycle is, it may be better or may be worse. There's a graph that will answer that. We can go on. So the graph is one of the throughput graphs, which we're about to get to. So anyway, now I'm going to compare it to CSMA. First we'll talk about throughput. This goes a little bit of the way to answering your question, Roy. So this is with perfect capture. So this is something that can't exist. So this is a little bit like putting a unicorn on the board. But again, we have throughput per packet time. or just throughput, and offered packets, or offered load, right? So how much of the channel are we filling? How much throughput do we actually get? Now, if anyone's used to looking at these pictures, you know it usually stops at 1. We're going beyond 1 because there are multiple receivers. We can actually receive 2 packets at the same time, which means we can go beyond 100% actually achieve throughput. So this is aloha, so everyone should recognize that little dinky curve. So this would be aloha, that means you're just transmitting, and you have no capture, right? So it has a threshold of like 18.4. It's unslotted low. This line is that same curve with capture. This line is that same curve, but now we have 2 receivers doing capture. This line is the same curve with 3 receivers. Right? So we predict every single receiver we add, we're going to get more gains from capture. Now, like I said, this is ideal. So we have real numbers for what the capture is for a couple pieces of hardware. So these are them. These blue lines are 1, 2, and 3 receivers of CC1100, and these are 1, 2, and 3 of those Atheros cards, right? So this has a 6 dB capture threshold. This has a 1 dB capture threshold. So now, obviously, we'd much rather have the Atheros cards than the CC1100. But that being the case, if you add more receivers, you'll still get better performance, right? So even though we'll get, we do much better with something with a better threshold, the result holds that as you add more receivers, you should get better performance. So just to mention it, so this was actually the slide that would answer Roy's question. So for anyone else who was interested in it, he was asking what would happen if we change the load basically by doubling the number of transmitters and doubling the number of receivers. So adding more receivers moves us up these lines. Adding more transmitters moves us down these lines. So now these 2 things are exactly the same number of receivers, but what's changed is the duty cycle offered by the transmitters. So in this case, the transmitters are offering 0.5% duty cycle. So this is like a, let's say if you're transmitting a packet every second, these are, 5 millisecond packets? In this case, they're offering a duty cycle of 1%, so these are like 10 millisecond packets. So the difference here, notice the peaks are actually the same, so look at where the peak is here. The peak is here. And I know James asked me to draw a picture of this, I didn't have a chance. This is in a different place, or the best performance is in a different place because of when you're most likely to see a collision involving some number of transmitters. Right? So once you make it more likely that some number of transmitters collide, which is probably around a little bit more than the number of receivers you have, your performance starts going down. That's where
So I might be missing something. That means if your duty cycle goes up, your throughput actually comes down.
Well, no, it depends where your offered load is, right? So if your offered load was...
Okay, when your duty cycle goes up, your offered, given the same offered load, your throughput is higher. Okay.
Yeah. So it depends. Like, so let's say we had an offered load of 2, and we changed our duty cycle, and at the same time changed the number of transmitters. In this case, a higher duty cycle would give us better throughput.
Okay, so that means the duty cycle is still small. If you go to a really large duty cycle, things will be different.
Yeah, if you had a really, really high duty cycle,
Like
it would
10%
pull everything
will
to
be
this side. Basically, you'd reach peak performance very quickly and then start to degrade, which intuitively makes sense because then you have nothing but constant collisions.
So to ask Roy's question again, but to ask your half of his question, if you raised to 216, but kept the duty cycle the same.
But kept the duty cycle the same. It depends where you are on the curve.
Would these curves stay the same?
The curves would stay the same, but depending on what the duty cycle is, you may or may not be at your peak level. All right, so let's say in that other one, it would look like this, and we had an offered load of, like I said, I think it was like 30%. Doubling it, right, would shift some direction on these lines. So in that case, a higher load would, if we had a higher load from each individual transmitter, we get better performance, or better total throughput. It's total throughput that you're getting up packet loss rate. In this case, with lower duty cycles, you wouldn't get as much throughput because you're not at peak performance yet. You're still building.
So then duty cycle is just the time that you're awake versus some period.
So this is like radio duty cycle. So how long is the packet versus how often you send it? So I'm assuming a periodic transmission.
Oh, just transmission versus, because I mean there are different.
Yeah, there are different ideas. So here by duty cycle, let's say we have a duty cycle of 0.1%, that means your packet duration is 1 millisecond, then you sleep for the rest of the second. And then you wake up and you send a 1 millisecond packet, and then you go to sleep.
So packet interval is just the transmission time?
The packet duration is the transmission time, and then the interval is how much time you sleep between packets.
Oh,
Okay, so anyway. So let's compare TO to CSMA. So let's go back to the ideal one for a moment.
So why do you compare it to CSMA?
Because it turns out for a lot of the low power things, CSMA actually ends up being the best. So there are a lot of protocols, which I've written about at length in the thesis, like low power polling, EMMAC, WISEMAC, YMAC, SCP, AMAC, BMAC, crankshaft. So there are a lot of them. And they all do lots of different things, but for the most part, there are two things they really do. One of them is they do some kind of timing, or they do some kind of carrier sensing. Now the one that won like best paper, and I think Mobicom or Mobihawk a couple of years ago was called EMMAC. It was really great. It kept a duty cycle like of 0.01%. It was super, except when you turned it on, it stayed on for 30 seconds to figure out what its timing should be. That means if let's say I was carrying a device like that, I come to the lab, it would spend 30 seconds adjusting. I go home and spend 30 seconds adjusting. If you remember from that power graph, at the very beginning of the presentation, I showed you have like 10 seconds of on time, right, per day with a coin cell battery. So those ones don't even work. So the carrier sensing ones actually do work very well. So a lot of people use CSMA in 802.11 beaconless mode. So if you take 802.11, or say 802.15.4, you turn off beacon mode, and you just use CSMA without time slotting, that's really power efficient according to current literature. That's sort of what's popular now. That's about what everyone thinks is pretty good.
is it true even for the saturation regime?
For which one?
Saturation when you have a lot, when it scales to a large number of milliseconds.
It is. So P persistent with a very low P will do very well. Right? So that's, you sense the channel is empty, and then you probably don't transmit because you assume that somebody else probably will. The problem with the TDMA systems is that a lot of them are, if you have an offer load over 100%, the TDMA systems, somebody has to be ejected, right? Somebody doesn't get a time slot no matter what. And so they spent all that time figuring out the timing, and they got nothing from it. So once you hit some load, they're not very efficient. Same thing with like low power polling, which is a method where you turn on, where the receiver turns on a long beacon. Everyone else is sleeping. And they turn on periodically to listen to the long beacon. When they hear the long beacon, then they'll send a packet out. Now the problem is, it sort of becomes very similar to CSMA. You listened all this time to hear that beacon, and then you got it, but you probably don't get the channel anyway, right? So a lot of those systems, they're, in the end, the best ones are very similar to CSMA in power, and none of them are all that much better than CSMA. So P-persistent CSMA is sort of the most consistent one across all of them. There are particular ones that we could have looked at, but for there are standards like BLE or ZigBee aren't even anywhere near this in terms of power efficiency. So that's where we're looking at CSMA. All right. So this is again throughput, offered load. So this is 0.01 persistent CSMA, so when it senses a channel is idle at the end of a packet, so it turns on, it listens, it sees that eventually finds an empty channel, it will transmit with probability P, which is 0.01, which means that only 1 in 100 times that it senses it's idle does it actually transmit. So 0.1 persistent CSMA with a 10% chance will transmit a packet. So actually, CSMA gets pretty good throughput. It's sort of a fairly well-known result that CSMA is pretty good, and some people have done some things to prove that CSMA is, for some word optimal under some conditions. So now TO. So now, again, these are the 3 lines that we saw before. TO with 1 receiver, 2 receivers, 3 receivers. Right? So what I'm trying to show here is that as we have receivers, we can do better than CSMA can. Which we should already know, because I showed before that we could clear 100% channel throughput, which CSMA simply can't do. Right? Sitting on the same channel, CSMA just can't do that.
But is that fair comparison?
Well, no, in some ways it is. CSMA can't do it. Right, so the other, there are other multi-channel protocols, like BLE is multi-channel, but BLE takes a large amount of energy in the setup phase. Same thing with EMAC was the one I was describing that takes 20 seconds every single time it turns on, 20 or 30 seconds every time it turns on. Right, so spending 20, 30 seconds just because somebody moved from one room to another is sort of cost prohibitive. So a lot of the multi-channel protocols aren't very power effective.
But BLE also has those 3 advertising channels where you can do frequency hopping.
Yeah, it does, but they have to rendezvous on a master channel first, and there are different master channels, but it's very costly. So the minimum transaction in BLE is 3 milliseconds. Right, so let's say I have 200 microseconds of data to send you. I have to stay on for 3 milliseconds. Right, so what's my energy efficiency there? It's pretty low. Right, especially, TO is really good, transmit only is really good because if we have very low offered load, like let's say you just have 10 transmitters, they just transmit, they'll almost never have a packet loss. Right? And let's say we have very high load, same thing, you transmit, as long as you have enough receivers, probably a very low packet loss. It sort of makes TO suitable for a very large range of offered loads. And just, if you are designing a TO system, if you know how many, let's say each of us had a transmitter, if you know how many people fit into a room, you could adjust the number of receivers to your expected load, right? Which is something that these other systems have a lot of trouble doing, right? You can't, you could have a CSMA thing that adjusts its peak persistence based upon the load and environment, but this involves more sort of communication with everything else. And you can do that. You can have, see how many packets you lost, see how many acts you missed, and then you can back off, do sort of TCP-like, control, but it makes it much more complicated. Whenever you make anything more complicated, you have to pay energy for it. Whereas with TO, each transmitter never has to worry about it. It doesn't care anything about, did my packet get through, did it not, it just does the same thing. It allows us as the engineers who are designing the actual topology and deployment, we can determine what performance we want and deploy receivers to achieve that performance. So that's the way I think.
I want to make sure I understand something. At the beginning, you defined perfect capture as a situation where a receiver can receive a packet even if the signal to interference ratio is 0 dB.
Yeah.
But here, you're defining perfect capture as a receiver being able to pick up at least one packet, no matter how many are arriving simultaneously.
Yes.
Okay, that's a little bit different because if you have 10 packets that arrive simultaneously, your signal to interference ratio is approximately negative 10 dB.
Okay, so I'm not counting the actual analog combination of signals. So I also don't count if you have one thing that's 10 dB stronger than 100 weaker transmitters. I don't count their actual additive interference. So I'm not doing that. It was a little bit beyond the math I did. So yeah, there are cases where this is slightly simplified. Okay. So anyway, same unfair comparison. We have, but this time, energy efficiency instead of throughput. And notice this is on a log scale. So obviously, as we offer more packets, so as our offered load increases, we're going to do worse in terms of efficiency, either because of packet loss or for CSMA because you're backing off more often. But again, the nice result here with TO is as we add more receivers, we do better in terms of energy efficiency because our packet loss goes down. What's up, Rich?
So I want to push on this idea of unfairness. So in some ways it is fair, because there's underlying assumptions about what's fair.
Well, I think it is a fair comparison because, in terms of you were just setting up a network and you had to choose between one or the other, you have to. This is the kind of comparison that you could do. And there are different MAC protocols that you could choose that might be specifically suited to one specific kind of deployment. But both of these are sort of general purpose protocols. So if you're just going to use a general purpose protocol without designing one specifically, then this is the kind of comparison you do. It is true, like let's say you were in a power plant and you wanted to achieve definite guaranteed packet reliability, you'd have a protocol designed to give you high packet reliability, and maybe you'd have certain packets have higher priority than others and they're routed differently. You might do stuff like that. But this is a very sort of general purpose kind of thing. With TO, you could also have like high priority packets that, let's say, switch to a high priority channel.
Well, what I was pushing on a little bit is, to reason about what the denominator isn't fair. Okay? So, right, if you assume that transmitters and receivers are somehow the equivalent amount of resource, then for each TO transmitter, you dropped a receiver. So you could add that onto your receivers as the total amount of resource.
Yeah.
Right? So in that sense, then you've actually saved a lot of resources because you eliminated all those receivers from your system. Right? Over a CSMA system that would have to have a receiver for every unit. Just,
Yeah, but that's weaker receiver. This is much stronger, right?
I'm just saying that TO, it depends how you count the denominator.
Right.
That's all.
So there are many ways of looking at it. Let's move on.
I have a question. So energy per bit, are you
Energy per successful bit.
right, so are you kind of the energy consumed by the receivers, or just the transmitter?
No, not the receiver, just the transmitters. Right, so this doesn't, again, I said I assume the receivers either have huge batteries or they're wire powered. Right, so their energy is free. So that's why we can keep adding receivers and so forth. So let me show you those same last two curves, but now with the Atheros wireless card. So again, where exactly this peaks does depend on the offered load, but it's a fair graph to show performance. So again, now with 3 receivers, we're not quite as good. We have to go to a 4th receiver, right? Because the Atheros wireless card doesn't have perfect capture rate. It needs 1 dB difference. But we can still do it. We can still get better performance. Right? So the point here is that we can always add another receiver, and at the offered load of basically 300%, which is a huge offered load, it shouldn't cost you that much to add a 4th receiver. Right? So the point here is that just adding a few receivers will always keep improving our performance.
Are there spatial constraints to how many receivers you can add? Isn't there some sort of upper limit to, after a certain point you stop intruding on
I guess the
space?
physics one would be like a wavelength.
Right.
And the realistic one is how many wires you can run. Because obviously at some point you'd stop running more wires for more receivers. It wouldn't be practical. But in terms of physics, you can, there's a difference in power level. As if one was 1 wavelength away and the other one was 2 wavelengths away, theoretically. So you should be able to add lots of receivers for the transmitters. So this is again same thing, but now with energy efficiency. So again, 3 receivers is only just barely as good as CSMA. You go to 4 receivers, we're a little bit better over here. Go to 5, it would keep going up. So again, it's consistent results. All we have to do is add enough receivers to get the performance we want. So again, that's the nice thing about TO. You decide what level of performance you want. You just keep throwing receivers at it until it's fixed. And if you start off, let's say, with some load, and then you realize that, oh no, let's say you build a stadium, and you have sensors in every seat, and then you decide you're going to add more seats. Right? So the nice thing about TO is you just add a few more receivers, and you'll get the same performance. Right? Whereas with other systems, if it was designed specifically for some performance threshold, you might not be able to change it so easily. So I think that's a very nice property of TO. All right, so now I did a few real-world experiments to demonstrate that all those plots aren't just hooey. So one of the things we wanted to look at was how do we actually choose where to place the receivers. And at some point, does the number of receivers we need grow to some impractical amount, which was your question. So let's talk about how we choose receiver locations to get the best capture performance. Right, so the actual equations are a little bit complicated. It's hard to tell where the optimal performance is. So we want to find sort of one metric to optimize. And that metric is going to be contention. Right? So we're going to say, let's say we have 3 transmitters and 1 receiver. Right? So contention would be the number of other transmitters who would cause you a packet loss if you transmitted at the same time. So now for transmitter A, if that one's transmitting to the receiver, these other 2 transmitters are much weaker than it. So it's not actually contending with anyone for the channel. If it transmits, its packet will always be successful. So it doesn't actually have any contention. Transmitter C, on the other hand, is much further away than A and B. So if it's in a packet collision with either of them, it will lose its packet. So to it, it's in contention with 2 other transmitters for the channel. So what we want to do when we choose receiver placement is to limit the contention. Right? So this way we don't have to worry about how often they transmit. We don't have to worry about how long the packet intervals are. We don't have to worry about any of those things. We're just counting contention. So this was some work that Rob and I and Junichiro Fukuyama did. So what we do is for every single pair of transmitters, let's say we have 2 of them, if we want to make sure that this transmitter's packet is captured when these 2 have a collision, we could put a receiver anywhere in this circle. So we call this circle a capture disk. So now let's say we wanted to choose good places to put receivers. So if we have a few transmitters here, let's say we have 3. For every pair of them we have a capture disk, so we have 6 different capture disks. Now anywhere in the capture disk is equivalent, so we just choose one solution point in the center of each disk as a possible place to put a receiver. There are also places where the capture disks intersect one another. Those are other possible locations because these locations cover 2 capture disks at the same time. Right? So then we put down a list of every single possible good place to put a receiver. And then we sort of greedily pick them one at a time. So whichever one covers the most capture disks, we pick that one. We remove all of those capture disks, and then we go on. We pick the next best one, and then we remove all the capture disks it covers, and then we go on. So it's a greedy approach because the problem looks very NP-complete-like. So we didn't choose it was NP-complete, though. Or we didn't prove it was NP-complete, so nobody asked about that.
I'm not going to ask about it. If I was building this, which would I pick first? The position of the transmitters or the position of the receivers?
So here we assume that probably you know where the transmitters are going to be, and you're building the topology of the receivers to accommodate that. Because probably whatever you're tracking or monitoring, you don't have a lot of control over where exactly the transmitters will be. It would be also possible to sort of do the other way, to try different locations of transmitters with a given set of receivers. But then there are more locations to look at, so that might be tougher. So anyway, so we simulated this. So this is the contention level in the system as we add more receivers. So we simulated a group of randomly uniform transmitters within a square. And as we add more transmitters, we look at what the contention level is at different numbers of receivers. So one nice thing is that receivers sort of keep the contention level, or they reduce the contention level sort of by a set amount, no matter how many transmitters you add. And that's just sort of the way the statistics work out because it's uniformly distributed. If it wasn't uniformly distributed, these lines wouldn't be flat.
I'm sorry, you said the transmitters here were uniformly distributed?
Yeah.
Okay.
So let's say they're uniformly distributed in the square.
Okay.
Not the receivers. So these are the receivers. We're choosing the placement for the receivers.
Okay.
So one thing you should notice is there's diminishing returns. As you add more receivers, you get less out of it, which should make sense, right? So if imagine we have an area, each receiver you put out covers a certain number of transmitters very well. It doesn't cover others very well because they're far away. As you add more receivers, at some point, wherever you put the next receiver, it's close to another receiver, so it does less work. So you get diminishing returns as you add receivers.
Have you heard about this Conway game, the kissing number? I think about 6. I guess that's it.
Oh, it's probably related to that. It's the same thing, that there's some number that you can fit into a space.
It's a backing
Yeah.
Does it matter here how big the square is?
No. Well, so we're assuming that everything is within range. The transmitters are all within range of the receivers. If we assume some things were out of range, then it would matter. But here we assume that everything's within range. So one thing to keep in mind is this is contention, not packet error rate. Each receiver still keeps reducing packet error rate. It's just that when you reduce it, right, going from 7 receivers to 8 receivers might reduce it from 2% to 1%, but that's much less than adding the second receiver after you just have one and going from like 80 to 90%. Right? So each one still gives you a gain, just the gain is shrinking every time you do it.
You're running out of area.
Yeah. So again, the question that was asked is, how many receivers do we have to keep adding? So that actually depends on if you have some desired contention level for the system. Basically, let's say you want to maintain some packet loss rate as you add more transmitters. And so this is the minimum number of receivers to maintain some contention level. This is the growth of the number of transmitters. Right, so this is, let's say we want a desired contention of 10, which is basically as we add more transmitters, we want each transmitter to exist in an environment where it's as if there were only 10 of them. Right, so that's when we get to 1,000 transmitters, we want this transmitter to think there's only 10 transmitters it's competing with for the channel. So obviously in this case we have to add a lot of receivers. So when we get to 1,000 transmitters, we're close to 50 receivers. But if we're happy with just having a contention level of 100, which means you're like competing with 100 transmitters for the channel, growth is much smaller. Right? So this is, again, this is a very quick way to see whether or not TO is suitable for your application. Right? So if you know what packet reliability you're okay with, you know how many transmitters you're going to have, then you can simulate and check very quickly whether or not the number of receivers you have to add is impractical. So this is a simulation of a non-uniform topology. This is a ring topology. So let's say the transmitters are arranged in a ring. Maybe this looks like a stadium. People are all sitting around something. So this is a placement chosen by our algorithm. So each of these little dots is a transmitter. These triangles are the receivers. I know it's not that clear here. Should have found a color version of this. And there's lines from each receiver to each transmitter showing how well it covers it. So this is the same thing, but this is the placement that you might do to get even signal strength across everything. Just sort of the placement that you might do if you're, let's say, trying to get even signal coverage for your Wi-Fi hotspots. So notice that this is very fair. So this receiver gives obviously very fair coverage to all these transmitters. But because it's fair, it's actually worse for the capture effect. If all of these transmitters have the same signal strength that this receiver, it means none of them will be captured. So it's actually very bad placement to exploit the capture effect. Whereas putting the receivers in amongst the transmitters is very good for the capture effect.
So I remember we actually asked Ivan or James, how should we place these three receivers?
Yeah,
That's
you also asked me.
Yeah, we were just
and now that I can fill in on some of the facts.
it's too late to change your mind. It's far too late. So one thing to note here is that this is unfair placement. So this transmitter, for instance, has really bad statistics. It's sort of left out in the cold. So if you really wanted to cover this well, you'd probably add a fourth receiver over here. But anyway, when we look at the average transmitter contention, as we add transmitters, we see that actually in this case, we're already doing as well as this one does with three transmitters when we only, or with three receivers when we only have two receivers over here.
Well, the total channel throughput went up, but somebody got.
Yeah, somebody. Well, actually, no. This one's not necessarily that much worse than these ones, right? So if all of these ones collide with each other, and let's say, this one may just be as bad as they are over here, right? But it's not necessarily the worst. It is worst out of all these ones, but when you compare it to these ones, it's not so much worse, right? So this situation is definitely better than that situation.
For overall throughput.
Yeah.
For overall throughput, and the very worst of these is not so much worse than the worst of these. That's what I'm saying. So even though it is less fair, it's less fair because some of these do really well, not because any of these are doing particularly well. Just all of these do the same amount of bad.
Is this what spawned that 1% comment?
No, that was something else. That was last minute paper submission delirium. All right. So now we also went outside and did a real world test. And we forgot to take a picture of ourselves when we were doing the sine wave experiment, so this is a uniform one.
We actually do have pictures.
Do we? I don't have them.
But this looks much nicer. So.
Okay. So anyway, we went out into that empty field out there and we did some radio experiments. We arranged the transmitters in a uniform distribution along a sine wave pattern. So what we did is we treated this as a line and we chose random locations within the line to put them. So these were all the transmitters. So now to choose even signal strengths, we arranged the receivers in the line, and then for our placement, we ran our algorithm to choose receiver locations. Packet duration was 1 millisecond, packet interval was half a second, and we started with 200 transmitters, and then we started with 500 transmitters, and we went down to 200. That sounds better on paper. So the offered load went from 0.2 all the way up to 100% offered load. So this is just to show you that choosing the placement actually is better than just sort of a random place like that. Not a random placement, but sort of a fair placement.
Is it the sine wave or the uniform?
This is the sine wave. So again, this is the measured throughput, and this is what the offered load was. So you can see when the offered load is very small, the chance of a packet collision is very low. It doesn't make a difference. But as there are more and more packet collisions, our better receiver placement became more and more important, so that by the end, we were receiving around, I think, close to 93% for this one, and we were down at 88% with this one. So basically, one had 12% packet loss, and the other one only had 8% packet loss. So one did half again as worse when we just choose a sort of naive placement but when we replace it with our algorithm, we cut off 1/3 of all packet loss with only 4 receivers. Yeah.
But does that need to be tailored to your defined geometry shape?
Yeah. So you basically have to know where the transmitters are.
Circle or something.
Yeah. So if you know where the transmitters are, you can just run the algorithm and it works. If you know that you have like a random uniform deployment, like within a box or a grid, then actually you can deploy sort of any symmetrical shape and it will do okay because there's not a lot of structure for the placement algorithm to take advantage of. As long as you put them, the receivers not close to each other, like if you have 3, put them in a triangle. If you have 4, put them in a box inside it, that will work okay. So if you just have a random uniform deployment, then actually you can intuitively pick the placement. If you have a more complicated shape, then you could run our algorithm and pick the placement. Okay, so now we're going to do the math section. So in this section is all the math that we use to generate those figures. So
You probably want to go slightly faster in this section.
all right. So if anyone has to go to the bathroom, that's anyway. Okay, so let's go fast. All right. So capture occurs when we have some relative signal strength amount. We're going to call that's equivalent to some relative distance that's actually dependent upon the exact propagation coefficient in the area. And let's assume it's 1 over r to the alpha. So alpha is the propagation coefficient. We're going to call that relative distance k. It's going to range from 0 to 1. 1 would be perfect capture, which means that if they're at the same distance, they're both captured. 0 would be there's no capture. Right? So we started out with some nice ratio that looks like that. We simplify k is 10 to the minus delta over 10 alpha. Right? Here's a picture of L1 and L2. These are the distances I'm talking about. So the ratio would be this distance over that. That would be k, L1 over L2. All right? I'm moving quickly. Okay. Now, let's say we want to find out what the capture probability is. Well, let's assume that they're uniformly randomly distributed right now because otherwise it would be really hard to do. Now, the closest transmitter distance, let's say, is A. And by that I mean transmitters are all arranged in a uniform distribution in some cluster away from the receiver. Right? So let's say the closest one is A, the furthest one is B. Right? So now we're going to integrate over this to find out when that ratio of one distance to the other distance is less than or equal to k. Integral looks like this. Right? Now, there's a very nice simplification. If the closest transmitters can be to the receiver is on top of the receiver, which means basically, let's say we click a receiver and we put it in amongst the transmitters, then it simplifies to simply k over 2. Very nice result. Moving on. So, that's called delta, the packet duration of every single transmitter. That's called tau, the packet transmission interval. So every tau seconds is going to send a packet of duration delta. The probability of there being a two-way collision, that means a collision between one transmitter and another collision, is simply 2 delta over tau. Sort of intuitive to look at this. If we imagine that there's one packet here that lasts delta seconds, if any other packet begins transmitting delta seconds before it, or up until the end of it, there'll be a packet collision. So that's why the chance of a packet collision is 2 delta over tau. Now, what about multi-way collisions? Well, we can look at the probability that there is a collision across all n-1 other transmitters. Right? So let's say we have n transmitters. I want to know what's the chance that this one succeeded. What's the chance that it didn't have a collision across all n-1 other transmitters? Great. Now, let's say we want to know whether or not it succeeded when we take into account that there are multiple receivers and different probabilities for capture. Well, we have to worry about how many transmitters were involved in the collision, because obviously if we have more transmitters than receivers, capture can actually occur. So it's a very simple binomial probability here. So it's a summation for every single number of collisions, all the way up to n-1 collisions. So the probability of having that many collisions, probability of not having that many collisions, number of ways we can have that many collisions, and probability that it wasn't actually captured. So what's the probability that it couldn't be captured? I forget what it says over here. So if it's perfect capture, all we want to know is whether or not this one is the one that got lucky, right? Which is 1 over n, right? So if we have r receivers, it's the chance that it didn't get lucky over r receivers is 1 minus 1 over n to the r. Now, that's when the probability of being captured is 100%. There's always a capture. What if it says not always a capture? Well, it's 1 minus the probability that this one was the strongest, and the probability that strongest one was strongest enough than all the other ones that was actually captured, raised to the r at each receiver, which is 1 minus k. Remember that threshold from 4 to the n-1, because it has to do it against all other n-1 transmitters that it was in collision with, over n to the r. So in summary, transmit only sacrifices packet delivery guarantees for energy efficiency. What it's doing is it's giving you a probabilistic delivery. Now it also delivers very good throughput by exploiting the capture effect. So we saw before that it gives throughput as good as CSMA, but without any kind of delivery guarantees that CSMA can give. So we also presented a very nice model that we just walked through very quickly that does everything from simple aloha without capture to multi-channel capture at any arbitrary capture threshold. We've also backed up our models with several different experiments in the open room floor and outside in the various places. So that's it.